will be the last piece of our gases unit. Gases is relatively straightforward. You're seeing quite a bit of review from honors, which should make you feel better. We are going to link partial pressure that we talked about last time with mole fraction. And last year you should have learned about mole fraction, where you can calculate the mole fraction of the solute, the substance that gets dissolved, or the mole fraction of the solvent, the substance that does the dissolving. Mole fraction is abbreviated with a capital X. Moles of solute over moles of solution. How would you find moles of solution?
Add the moles of solute plus the moles of solvent.
You got it. So you just add the moles of solute and solvent. So if they give you the mass in grams, you convert to moles. Solvent mole fraction would just have moles of solvent on top. Calculating mole fraction is very simple, something you would have looked at in honors, but linking it to partial pressure is what I want you to see here. And again, not difficult. So the same way you get mole fraction, you can do it with partial pressure of the gas in question over the total pressure. And we talked about how to calculate these last time. So if you manipulate this part of the equation to solve for partial pressure of a gas, you would just multiply the mole fraction and the total pressure, and that's what's shown here. So this question here that we'll work through, make sure you understand all of those concepts, but also how to explain, because that's something you'll see a lot of on your quiz, test, AP exam, etc. So in this problem, they want to know the pressure exerted by a mixture of two gases. We have 0.25 moles of nitrogen gas and 0.4 moles of helium gas. Those gases do not react with one another. The temperature and volume are specified. So first we want to know the total pressure. Then we want to know the pressure of nitrogen gas. So we want to know the total pressure, the pressure of nitrogen gas, the mole fraction of nitrogen gas, and then be able to explain that last piece. So let's take it step by step and get the information down. We want to know the total pressure, the moles of nitrogen gas is 0.250. The moles of helium is 0.400. The temperature is 300 Kelvin. Now that was initially given in 2 sig figs, so my answer is going to come out in 2. The volume is 3 liters. I want to know the total pressure. I want to know the pressure of nitrogen gas. I want to know the mole fraction of nitrogen gas. And then I want to explain why the pressure of helium is greater than the pressure of nitrogen gas. That should be a 2. All right? How do we solve for total pressure? You could add the partial pressures. That's one way to do it. You don't have both partial pressures though, but you could get them. Add up the number of moles. That's what I think I would do. I would do total moles RT over V. So what's the total moles?
0.65.
You got it. Just add the two together. R. And R is given to you. You don't need to memorize it. Make sure you're in Kelvin or you're done. The volume needs to be in liters as well, otherwise it won't cancel with the unit as part of R. So you have 0.65 times 0.021 times 300 divided by 3 and your total pressure is 5.3 atmospheres. And there's really nothing to that, nothing you couldn't have already done. Now let's try and get the pressure of nitrogen gas from mole fraction. So the pressure of the nitrogen gas is the mole fraction of the nitrogen gas times the total pressure. So how do we get the mole fraction of the nitrogen gas? Go ahead, Sam.
You take the moles of the nitrogen gas that's given over the moles of the solution, which we found out before, which is 0.650.
What's the unit for mole fraction? There is none. They do ask for that piece, so I'm going to yank that out now. And the mole fraction is 0.385, no unit. And to get the partial pressure of the nitrogen gas, we're going to multiply that by the total pressure that we got previously. There's more than one way to do it, though. And I get 2.0 atmospheres. Now, why would the pressure of the helium be greater than the partial pressure of, why would the partial pressure of the helium gas be greater than the partial pressure of the nitrogen gas? Because you have more moles, excuse me, of the helium. And we know that pressure and moles are directly related. Be very comfortable with your variables. You can see here, you'll see a lot of this in your practice quiz. We know that pressure and volume are inversely related. We know pressure and temperature are directly related. We can throw molar mass into the mix as well. We know molar mass and temperature are going to be direct, pressure and temperature direct, etc. So be very comfortable with all of these variables. Understand relationships.
Why did you multiply that with 5.3 instead of dividing? Because isn't it
You want to know the partial pressure, and mole fraction essentially is moles of that gas over total moles, or partial pressure of the gas over the total. So if I want this piece, I've got to multiply this and this, correct?
Yeah.
So I did multiply.
Okay.
That is right there.
Thank you.
Does that make sense? All right. Piece of cake, yes?
Mhm.
The questions that they absolutely love to give you in May, that I just not my favorite, but relatively straightforward. These are examples with molecular representations. They're starting to call them more particle or particulate diagrams now. I think they're using that term because sometimes you don't always have molecules per se if you're dealing with an ionic compound. Nonetheless, calculate the mole fraction of gas B. What would you do? Go ahead, Sam.
Well, how much does each thing represent?
It's just, that's one, that's one, that's one, that's one. So there are 4 of gas B.
So you would get the 4 moles of gas B, and then you count up how many moles there are in the entire solution, and then put 4 moles over that.
Exactly. And the only thing I would recommend, and this is why I let you write on your quizzes and tests almost the entire year, is slash as you go. I've got to pull this down a little because I'm not tall enough, especially sitting here. but you know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, I don't know, how many are there? I lost my count. 16, awesome. 4 over 16 is a quarter, or 0.25 would be your mole fraction. Piece of cake, yes? Why would gas C exert a greater pressure than gas A, or does it? How many C's are there? 1, 2, 3, 4, 5, 6. Why would gases A and C exert the same pressure? Same number of moles, right? All right, piece of cake. The collection of gases over water is what you're going to do in the lab today. Many of you in honors, I'm sure, did gas labs that involved such a thing. I'll illustrate it based on something you're probably more familiar with, but you're going to see some of this in the lab today anyway. When you want to collect gases, collecting them over water is a good way to do it, because we know just to try and collect gases in this room would be very difficult, because in the air you have nitrogen gas, oxygen gas, carbon dioxide, and other schmutz that's in the air. So you would collect all of those gases as well. So typically you collect gases over water. And one of the things that we did in honors was that we had a trough that was filled with water. And we had a graduated cylinder, and we filled it to the tippy top with water, and then we put some type of protective covering that wouldn't leak, and we flipped the graduated cylinder upside down. Keep in mind it still had water in it. Then, if you take a lighter underneath the mouth of the upside down graduated cylinder and you push down on the trigger, the gas particles would go up into the graduated cylinder, displacing some of the water in the graduated cylinder. And so I'm going to raise this slightly because I wrote too big. And over time, you would collect gas. So let's say this is gas. This is water. And it is very important that the water level inside the collecting apparatus and outside is even. That's the way you're going to equalize pressure, such that atmospheric pressure, which you can get off the internet or using a barometer, is equal to the total pressure of the system, provided that you have those water levels equal. First of all, why is the gas sitting atop the water? It's less dense. You got it. Very straightforward. One of the things you're going to see when you do the lab is you're going to see these bubbles, evidence that a chemical change has occurred. In addition to the gas from the lighter, which is butane, what other gas do you find in this region? Water vapor. Because water evaporates at any temperature. So some of the liquid water here will vaporize into the gaseous state. And so in addition to the gas particles, you will have a little bit of water vapor. And you have to account for that. So the total pressure will be equal to the pressure of the gas plus the pressure of the water vapor. Now the pressure that the water vapor exerts on the walls of the container can be determined based on the temperature at which the experiment is run. And you'll see that in your lab. For example, I think you probably used it for the pre-lab. if you know the temperature at which the experiment is run, typically room temperature, although it's a little cold in here, let's say 22 degrees Celsius in here, maybe even 21 because it's freezing. This would be the partial pressure of the water vapor in millimeters of mercury. So from the temperature you can get the pressure of the water vapor. You'll know the total pressure because that'll be atmospheric pressure provided that the water levels are equal. How would you calculate the pressure of the gas? Just subtract total minus the pressure of the water. And that was in your pre-lab that hopefully you were able to complete with ease. The question asked in your notes, and I went over everything written in one there. So this is Dalton's law of partial pressure, which we've already talked about. You'll see the difference right here between honors and AP in regard to this question, and it's not difficult. A mixture of hydrogen gas and water vapor has a total pressure. Now it may just say that atmospheric pressure is 738 millimeters of mercury. If the partial pressure of water vapor is 17.5 millimeters of mercury, calculate the mole fraction of the hydrogen gas in the mixture. So let's take a look at what they've given us. The total pressure is 738 millimeters of mercury. The pressure of the water vapor is 17.5 millimeters of mercury. They want to know the mole fraction of the hydrogen gas. How could we determine the mole fraction of the hydrogen gas?
Finding the partial pressure of the hydrogen gas and then dividing it by the total pressure.
Absolutely. So what you can do is you can get the partial pressure of the hydrogen gas by subtracting these two. You get 720 millimeters of mercury, and then the mole fraction is just the pressure of the hydrogen gas over the total pressure, and there's going to be many more moles of the gas you collected than moles of water vapor, and you get 0.976. So again, at the honors level, they just would have asked for this. But now you can just make it a little more challenging, nothing that's going to blow you out of the water, and ask for mole fraction. Easy, easy? Alrighty. We had talked about the kinetic molecular theory at the very beginning of the chapter, and we said that gases are a collection of particles. They move in a rapid, random, straight line fashion. There are no forces between molecules. The molecules of a gas are very far apart. Essentially, their volume's negligible, and collisions are elastic. We also said that temperature is a measure of average translational kinetic energy, and that if gases are at the same temperature, they will have the same average kinetic energy. We're not going to get into too many quantitative aspects here. That seems to have gone by the wayside. Again, the average translational kinetic energy is directly proportional to Kelvin temperature. You don't need that formula. So all gases have the same kinetic energy at the same temperature. Now that's not the same speed, but the same average kinetic energy. In regard to molecular speeds, you don't need this anymore, but I will say, and we'll explore this in more detail in a few minutes, the lower the molar or molecular mass of the gas, as well as the higher the temperature, the faster the molecule will move. And you can see that from the relationship shown here. but they don't even give you that formula anymore, so it's not something you would have to know how to manipulate, and we'll see why. You know, as the temperature increases, velocity of particles increase, and we'll talk about molar mass in just a second. Maxwell-Boltzmann distribution, I do want to go over. That's something they do like to ask you in May in regard to multiple choice type questions. I've provided you with 2 handouts. This is the first one on the screen. The second one is the Pogel packet, and again, this will help you tremendously in understanding the Maxwell-Boltzmann distribution. In regard to the first handout, what we're going to start with is whenever we're talking about gases, we're not talking about a single atom. Rather, we're talking about huge numbers of atoms or molecules, and so we're going to need to rely a little bit on statistics to understand how the gases behave and how they interact. Boltzmann and Maxwell talked about this statistical relationship with gases, and that's what we're going to look at here. The first graph I'm showing you, well, you tell me, what does that graph show? What can you see in that graph? At 100 degrees Kelvin, a whole lot of particles are moving at a slow or a fast speed. Slow. But they don't all move at the same speed. What happens when the temperature is increased? So you're finding at the higher temperature, some of the particles can attain a much faster speed, correct? Now the area under each curve is the same, so that doesn't change. So as you increase the temperature, particles can achieve a greater speed. And if you were given a graph without the temperatures, you know as the temperature increases, the curve moves to the right and flattens out. This is going to be based on recognition. I'll give you an example. I think it's actually in your practice quiz. This particular graph shows you that as the temperature increases, you're at 0, you're at 25, you're at 100 degrees Celsius, the curve spreads to the right, you're moving to the right, and the value of the most probable kinetic energies will decrease. So again, a movement to the right and a smushing down. If you consider this now and you draw this red line here, you'll see that the fraction of molecules with energies greater than the red line increases. So this is the 100 degree, this is the 25, this is the 0. And if you consider the probability now, you have a greater probability at a higher temperature of higher kinetic energy. If I said to you which curve corresponds with the lowest temperature, it would be this one, highest temperature. And if you were asked to draw it in, could you do it? Keep this in mind, and let's look at the Pogel packet. First thing we're looking at is helium at different temperatures. And what do you notice? As the temperature increases, you're seeing that the particle speed is increasing. You have more particles with a greater particle speed at the higher temperature. So you're seeing a similar distribution. It moves to the right and it flattens out at the higher temperature. Now, some of the kids look at this POGO packet and they're like, you have to be kidding me. It says, what is the variable in unit on the x-axis? Some of the questions are too simplistic for you, but as you work through it, it will help with your understanding. It makes you measure, and that will be very good for you. Look at number 9. It says, circle the set of drawings below that more accurately illustrates the difference in particle speeds for particles of helium at 100 and 500 degrees Celsius. Be careful. Which one? Is it this set or this set? Why?
At the lower temperature, the arrows are smaller, saying when they go slower. And at the higher temperature, the arrows are larger.
Do all the particles have the exact same speed, though? Do all the particles have the exact same speed at the higher temperature? No, there's a distribution. So which one is it? It's the second one, and it's very tricky. Yes, average-wise, this is less, this is greater, but they don't all have the exact same speed. Be careful. We said temperature has an effect, as does molar mass. Take a look at this one. Why do more particles of xenon have a lower particle speed than those of helium? Because they have a greater molar mass. They move slower. And if you take the time to work through the packet, I think your level of understanding will be very high. What might you be asked? Something easy like this, as well as something easy like that. If you're given the picture, could you identify it? Could you explain it? Then you're set. The other two pieces I want to mention, one is all review, although I want to show you a little video clip because I've seen questions like this. The other piece is new, but it's very straightforward. Questions at this point? You're good? I think some of you could use some sleep. Yeah, I do. Alrighty. I went to school once upon a time.
Were you a band?
Played the violin at the top of my staircase. My dog hated it, and I gave it up. Oh, she hated it. It must have bothered her ears.
So that's how you gave it up?
Yes. I love my doggie. All right. Diffusion and effusion. Diffusion. Let's say, you want to do farting or perfume? Perfume. Let's say that Faith just douses herself with perfume over there. Who's going to smell it first? Shane. Josh, they're sitting right around her. But in the back, you won't smell it as quickly. But eventually, those particles will diffuse down their concentration gradient. They'll move from high concentration to low. And over time, you will smell it too. Diffusion is the movement of gas particles, or any particle, down their concentration gradient. This little video is very well done. Where is it? I'm sorry, I'm in the... Okay, get back there.
Yes.
No, get back there. Shh. What you have here is a glass tube. In this end of the glass tube, you have wet a cotton ball with ammonia. In this end, hydrogen chloride gas. And now the particles will diffuse down their concentration gradient toward one another. Let's look at the movement. Let's look at what forms. Let's look at which moves faster and where the substance forms.
Whereby molecules of gas move to completely occupy a space, getting a uniform partial pressure. In this example, gaseous ammonia and hydrogen chloride diffuse through air from either end of a sealed tube. When the two gases meet, a precipitation reaction occurs, forming ammonium chloride. The mass of the hydrogen chloride molecules relative to those of ammonia is greater. Thus, hydrogen chloride molecules travel more slowly. Diffusion is the process which
Well, I wanted you to see that band again.
hydrogen chloride molecules travel more slowly.
Okay. Why do hydrogen chloride molecules travel more slowly? Because they have a greater molar mass at about 36.5 compared to 17 for ammonia. How could you get a stripe or a solid? I don't really think that's precipitation. That's not my understanding of precipitation. Precipitation is when you have ions. But nonetheless, how could you get a solid stripe in the middle? The molar masses of the substances would have to be the same. Understand that. You get weird little questions like those popping up on AP exams. Not a hard concept, but sometimes it's just worded differently and it looks funky. Be careful. So wherever the stripe, if you will, forms, this substance has to be heavier, has to have a greater molar mass, moving slower. Effusion is the process by which a gas escapes through a tiny hole in a container. So for example, if you have a balloon, the gases escape. If you're bike riding and you go over a nail, you have a hole in your tire, the gases will escape. You also could find that now many of you are driving. Never drive through a construction site. You'll always get a nail in your tire. And there's other ways to get holes in tires, but they're probably not legal, so we wouldn't want to discuss them. We're on video. So here's effusion.
Fusion is the process of gaseous atoms flowing into a vacuum through a hole in a container. The rate of effusion of gas molecules at constant temperature and pressure is inversely proportional to the square root of the molar mass of the gas.
So the square root, inversely proportional to the square root of the molar mass of the gas. That is a mouthful. You actually know how to do this already. This is Graham's law from last year, where the velocity of gas A over the velocity of gas B is equal to the square root of the molar mass of gas B over the molar mass of gas A. Again, note the crisscross, the inverse relationship, square root though. Be very careful there. All right? Now, in regard to calculating here, I don't think you'll see much in the way of calculating, but do you understand the relationship? We'll walk through two problems. Which effuses faster when the two gases are compared under the same conditions, that is, same temperature, pressure conditions? Which one effuses faster, nitrogen gas or argon? Nitrogen gas. That has a molar mass of 28 grams per mole. Argon about 40. So for example, if you were considering molar mass of nitrogen gas, we'll make that approximately 28 grams per mole. Molar mass of argon is approximately 40 grams per mole. So clearly the nitrogen gas will effuse at a faster rate because it has a smaller molar mass. Now it says how much faster. How could you determine that? Why would you do that? You could set up some sort of proportion, but you're missing something. Your approach is good, but you're missing one key piece. If I tell you that the velocity of gas A over the velocity of gas B is equal to the square root of the molar mass of B over the molar mass of A, you tell me what you're missing. The square root. So be careful there. In addition, you want to know how much faster, so which one moves faster? Absolutely. Nitrogen gas moves faster. Go after that one. Set the heavy one, he's the slowpoke, at 1 meter per second to make life easy. So what you're looking for then is the velocity of nitrogen gas is equal to the molar mass of argon over the molar mass of nitrogen gas, and then you'll multiply that by the velocity of argon. So your proportion idea is good, although I'd put the heavy one on top. And what you've got then is you've got the velocity equal to 40 grams per mole over 28 grams per mole. And you're going to multiply that by 1 meter per second, really to just get the unit in there, and again, square root. So you've got the square root of 40 divided by 28, and that is going to be 1.2 meters per second. So the nitrogen gas moves 1.2 times faster than the argon. So it's the inverse relationship of the square root. Now, will you be asked how much? I don't think so. You need to understand which one moves faster and why. So you'll see on your quiz, I put, you're playing with two gases in this problem, and then I'm just branching the problem in multiple directions, and I'll say, all right, you have the two gases in there. You put a pin-size hole into it. Which gas effuses out faster and why? And you don't need this much explanation. You would say the nitrogen gas effuses at a greater rate because it has a smaller molecular mass. The end. No book. Boom, boom, done. All right? And we'll work on wording of answers probably more in the second 9 weeks once you're starting to get a groove. The second question is really more of an honors level question. I don't really see you getting this type of question, but I will mention it. It says, what's the molar mass of a gas that diffuses at a rate that is 0.67 times that of oxygen? So it effuses slower than oxygen, which means its molar mass is greater. Okay. So if you were working this type of problem, and again, this is an honors level type problem that you probably would have seen last year. If, for example, you want to know the molar mass of some unknown gas, I'm writing UNK for unknown. The molar mass of oxygen gas is about 32 grams per mole. Oxygen is, of course, diatomic. The velocity of the unknown is 0.67, and the velocity of oxygen we're going to set at 1 meter per second. Just be careful here in your setup. Whenever you're solving for something, put it in the numerator. It's so much easier. And then crisscross here. Velocity of the unknown, velocity of the oxygen. Now when you go to solve for this piece, what should you do to get the radical out? Square, but you got to square both sides, right? So then the molar mass of the unknown is equal to the velocity of oxygen gas over the velocity of the unknown squared times the molar mass of oxygen gas. So you've got 1 meter per second over 0.67 meters per second, and you're going to multiply that by 32. Don't forget to square it, otherwise you're going to make a mess. Make sure your answer makes sense. I'm getting a molar mass of 71 grams per mole. It moved slower, it should be heavier, and it is. And again, that's an honors level question. You'll see a couple homework problems if you need a little bit more help with it, and you will. You're not going to get everything in here. You've got to do some work outside. If you're trying to figure out what the gas is, when you look at the periodic table, 71 falls in here. Is gallium or germanium a gas?
No.
No. So it's a diatomic element. Which one? Chlorine gas. Easy? All right, last piece of the puzzle. New stuff, very easy. Super easy. All right, there was a whole POGL packet on this, and I looked at it, and it was very good, but it was to the point where I just thought I was pushing you over the edge. So I'm going to let you know exactly the type of question I think you might be asked. Real gases. When we talk about gases, we talk about ideal gases, the ideal gas law. However, certain conditions don't really allow gases to behave in that manner. And these conditions are exactly what you find in my classroom. High pressure, low temperature. There's no class more stressful. There's your high pressure. And there's probably no class more cold.
Mr. Mahar.
High stress too, it's perfect. High pressure, low temperatures don't allow gases to behave in an ideal fashion. We say they deviate from ideal gases, or they behave like real gases. Watch the wording. Some kids don't know what deviate means. What does deviate mean? Like go against the norm. Like a deviated septum, it's busted. So against the norm. At high pressure, molecules are going to be closer together than usual, and as a result, some of the volume is truly attributable to the gas. At low temperatures, particles are going to move slower, and as a result, some intermolecular forces will form. We'll revisit the IMF concept when we get there in the second 9 weeks. Here's your ideal gas law equation. Here's the adjusted ideal gas law equation according to van der Waals. Going to add a little bit to the pressure. We're going to take a little bit from the volume. So the pressure is too low and must be increased by some factor to account for IMFs. The volume is too high and must be decreased to obtain the empty space in the gas. There were 2 pieces from the POGL packet that I thought might be helpful. It's a little tricky. I'll let you read it on your own. You increase to adjust for the low pressure. You decrease to adjust for the high volume. These are the 2 types of questions that you're going to see. It says in general, I think. In general, the greater the molar mass, the more deviation from ideal behavior because the molecules move slower. Oops, I left the answers in. Explain to me why sulfur dioxide would deviate the most from ideal gas behavior. It has the greatest molar mass. Now, if the question said which behaves most like an ideal gas, the answer would be hydrogen gas with the smallest molar mass.
I didn't even see this one.
What?
I didn't even see D and E. I was just
Oh.
It's like this one.
Which of the following, well, I don't know why these got stuck in left field over here. Like, I tried to move them, but it was,
They're not on the other one. They're not. The Google Doc line.
oh, they just go wherever they want.
That's okay.
There we go. Is that better?
Yeah.
Betterer? This guy doesn't want to move though.
No.
Ugh. Can't have them crooked. All right. Which of the following best illustrates a real gas? Think about the class. It's cold and it's stressful.
B.
Low temperature, high pressure. Good. Now, which would best illustrate an ideal gas?
C.
C is correct. Alrighty? Don't foresee too much. For those of you very interested in this concept, we will talk a little bit more about the IMFs later in the year. I looked at the packet. If you want a copy of the packet, I'd be happy to provide you with one, but it was very long and really tricky. All right. Know the conditions of real gases. Understand diffusion and effusion. Interpret graphs for the Maxwell-Boltzmann distribution. If you didn't do that POGO packet yet, you better do it tonight. Understand mole fraction and partial pressure. Questions here. The gas chapter is relatively straightforward, and you will nail that quiz if you take the time to do enough practice problems. If you're going in with incomplete packets and an incomplete practice quiz, I wish you good luck. If you're starting to study at 10 o'clock on Wednesday night, you will be too tired to do well on Thursday. A little bit every day goes a long way. Be careful.